Okay, so let's explore this. So first, let's appreciate another way to describe what the diagonalizing unitary is. The diagonalizing unitary is really some object that eats product states and spits out eigenstates. That's what it is. It's a thing. It eats product states, it spits out eigenstates. And in fact, if you believe this claim that I've told you over there, what it essentially does is it turns zeros into g's and ones into p's. That's kind of an aside, but it eats product states, spits out eigenstates. Good. So let's imagine the following case. Let's imagine that without loss of generality, we'll say, look, it eats the product state all zeros. I mean, zeros think spin down, one thinks spin up. So I'm going to like jump back and forth between binary numbers and spin up and spin downs. Let's say it eats all zeros, and it goes ahead and it spits out the ground state. Okay. And so now, let's say I have an MBL phase, so it's many-body localized. So sort of roughly speaking, I should think that when I begin putting excitations into the ground state, that there's some localization to them. So I can imagine the following. I can imagine, look, one of my excited states looks like this. I have some local excitation that lives over here as part of the, that could be one of my excited states. And imagine I do the following. I say, look, let me just take that product state, 1, 0, 0, 0, and let me have my unitary operator map it to that particular excitation. Okay, so that's certainly legal. I get to choose any set of product states to any eigenstate to build up my unitary operator. And that will be a unitary operator that successfully diagonalizes my Hamiltonian. In spite of its legality, it turns out that this is a bad idea. So let's say, a bad idea if I want to build a quantum circuit that's of short depth. Let's say I want to play this game, and now I tell you, look, okay, go ahead and build a quantum circuit that somehow succeeds in doing this. Well, what you're going to have to do is you're going to have to put in some quantum circuit elements that go ahead and look at this product state up here. You're going to have some elements that recognize that I flipped this bit to 1. And then you're going to have some elements, right? These are just circuit elements. They're just length 2 or something. You're going to have some elements that go ahead and move just that fact, right, that I've gone ahead and flipped the bit on the left half of the system to 1, all the way over to the right half of the system. And then you're going to have some element that, conditioned on the fact, changes that right part of the system. So if I just tell you to do this quantumly, classically, whatever, this is what you're going to have to do. You're going to have some wire, some set of gates, something that drags itself across the system that says, oh, recognize that this has changed, you can change something over here. And this is bad, right? Because I really have to do this. What is that? Depth. Yeah, that depth is linear in my system size. That depth is n. But this is bad because somehow I've made a claim over here. My claim is that there's some short MPO, and I told you what that meant. Is that meant that that quantum circuit was constant depth, independent of my system size. And so here's a case where for exactly the same unitary, diagonalizing unitary up to some permutations of the rows and columns, I end up with something that's not constant depth, but that's linear depth. So what this means is that it's important not only to know that there is this unitary that diagonalizes the Hamiltonian, but it's important to choose for that unitary the correct mapping between product states and eigenstates, the correct permutation. If I were to say, look, that was stupid, what I want to do instead is I want to flip this bit to 1, and I want to map that to this eigenstate. Well, then I need essentially one quantum circuit, one gate, or a couple gates. And then this depth here is constant. And so it might be that in some cases I'm just stuck, that I can't get constant depth. But it's also the case that if I choose badly, I'm definitely stuck. I definitely have a problem. So that is important. Any questions about that?
We're
Yes, I'm saying if you mislabel your unitary, if you choose the wrong ordering of the rows, then when you turn it into a quantum circuit, it will be long, in spite of the fact that if you just had labeled it better, you would have had a short quantum circuit. Yes?
So are there, I'm just curious, so just more in the line with conventional DMRG, are there statements about sort of swapping the bases, not the bases, swapping essentially the local sort of sites, basically to improve the tightness of your product state. I've heard statements about this, but I never.
Yeah. I mean, any DMRG code where in 1D, it's obvious what the ordering of the sites should be in DMRG, but any DMRG code that's doing quantum chemistry or 2D or anything else has in it, like, as part of the input, like the ordering of the sites. And people in practice swap the ordering of the sites all over the place to improve their efficiency or bias or unbias their code towards particular states. So this is sort of a canonical thing to do, and it's morally speaking for the same reason.
But is it done essentially heuristically, or is there a sort of...
It's heuristically. There's no, as far as I know, there's no deep answer to the question, how do I choose this exactly correctly? Yes?
Is there a unique shortest step quantum circuit? And if there isn't, what does it mean when multiple circuits at the same depth?
Okay, so there is almost certainly a unique shortest step. Okay, there's certainly a shortest step circuit. Maybe it's not unique. Okay. I don't know that it's unique. It's probably not. Because probably you can do something simple like add a swap gate somewhere that doesn't have the depth. We don't know the answer to the question, how do we build the shortest circuit? Next time, we will at least see an answer to the question, what are heuristics to build shortish circuits so that we can make progress sort of in thinking about it.
Is there any importance or significance of having multiple?
No, I think there's nothing deep there. I mean, so to zeroth order, you can say, look, imagine I have like two excitations that are like this. Whether I map 0, 1 or 1, 0 to them, it doesn't really matter. So, no, I don't think there's any reason. Okay. In addition to the mapping of product states to eigenstates being important, it is also important that you don't screw up the signs. So, if I wanted to be cruel, I say, look, for every product state, what I'd like to do is I'm going to assign an arbitrary sign to the excited states. So I just have some product state binary number 0, I'll make sign +1, binary number 1, I'll make sign -1, binary number 83, I'll make sign +1. If I do that, for exactly the same reason it's a disaster, I have to go ahead and I have to look at my whole state to decide what number it is, and then I will be able to figure out what the sign is. So that's bad. You just want some simple rule, some like local quantum circuit rule that allows you to sort of look locally at the number and decide what the sign is. So one can make my depth linear again if I want to do something crazy with the signs. In fact, we know this generically. We know sort of one of the easiest ways to have a highly entangled state is just to have a sign structure that's essentially arbitrary. To zeroth order, that's actually why the entanglement of eigenstates are kind of large. And so this is, again, kind of a labeling problem. It's just sort of a more subtle labeling problem. If I have to look at my whole binary number, if I have to look at all the bits to decide what the sign is, then again, I'm going to have sort of linear depth circuit. So you see this in some complicated way. Good. Questions about that?
So when you were defining product state, so there was no sign. Where is this sign coming from?
Well, even for the product states, there's a sign. I could have said, over here I said my eigenstate was this, but I could have said my eigenstate was -1 times that. Also true. I mean, I can multiply my eigenstates by signs here and not affect anything.
That's an overall sign, right?
No, I can multiply each eigenstate by a sign. It's still an eigenstate.
But still, it will come out to be an overall sign.
No, I can multiply each one by a different phase or a different sign. So this happens in ED all the time, right? You get some ED vectors spit back by your computer, and you run it at a slightly different parameter, and the signs are totally changed. And you compute fidelities or something that looks like garbage. You do very phase calculations. You've got to worry about this sort of as a technical problem all the time. But here it's even kind of a conceptual problem. If you don't sort of choose the signs right, you're going to get a large quantum circuit. Good. Other questions? Yes?
Just a question of the voltage. When you start using somehow the T's and E's, and then you look for the circuit.
So the implication goes both ways. The G's and E's implies the circuit, and the circuit implies the G's and E's. At the moment, you're forgetting about the G's and E's, and I'm just going to argue for you that through some physics hand waving and numerics, that these unitary circuits are short. But to do that, I should first tell you that we have to choose sort of the labeling right for this to make any sense. And so all I've told you so far is that the labeling matters on these unitary circuits. And at some point, maybe not today, I'm going to get around to telling you why there's evidence that these quantum circuits that come out for these U's that correspond to the NBL Hamiltonians are short. I did study, but I am also reading.
If you think of these unitaries, if you think of the adiabatic continuity in the space of these unitaries, there's part of the trivial ones where the depth is 0. Then you realize that this process of keeping the configuration and spitting out a state, right? The time convention is not negotiable. There's no.
That's right.
Right, and then the idea is that, as you push away from zero depth unitary, you want to adiabatically sort of follow the sign convention.
That's right. You don't
Kind of
want to scramble the signs for no reason.
It's really a strong version of adiabatic.
Yeah, that's right. Other questions about that? Okay, so probably, since I am over, this is a reasonable point to stop. So what I'm going to tell you tomorrow then is we're going to kind of continue on just understanding what's going on here. I'm going to tell you, one, how we heuristically build short quantum circuits, and two, why some hand waving and numerics from this implies this GE structure. And then we're going to see why this also implies short L bits. Not short L bits, just L bits at all, local Hermitian operators, and we'll see why the other application works as well. And then, for whatever time is remaining, we'll describe algorithms that we can actually use, instead of just sort of a conceptual language, algorithms for understanding, for getting our hands on these eigenstates. We know that they have this beautiful structure. It seems like we ought to be able to get our hands on them, and in fact we can.
And the radio.
Thank you.
Thank you for the lecture.